Good morning. So we've made it to the end of our first full week, kind of a week and a half, I guess we could call it. So I just want to update where we're at. So we are here today going to discuss average rate of change. And this is where we're going to kind of make this transition between just some theories that we've been talking about, limits particularly, and why we are talking about limits. For the most part in this course, we don't need to calculate limits, but we need to believe in limits. So I said this is where math is almost like a religion, or you have to have faith in some things. And you think math, why would you have to have faith? 2 + 2 is 4. I can show that. But the thing is we're going to talk about something called the derivative, which is the slope at a point, which doesn't make any sense because all our lives we've been getting the slope at 2 points, right? You connect 2 points and you get a rate of change between those two. That's what we're going to get into today. But I'll show you how we're moving with when we apply this concept of being able to take the slope, have 2 points, connect them with a line, and get that slope of that line, how we're able to slide those 2 points and make them into 1 point and still get the slope. But to do that, we need to believe in limits. We need to understand limits. We need to see that limits really do work. When we get to this place where something doesn't exist, if we come close enough to it, we can figure out what it would be if it really did exist. And that's the cool thing about math, is there's all these things that don't physically exist, and yet they're useful for us. Imaginary numbers. How many of you you've heard of imaginary numbers, right? That little I thing, because the square root of a negative number. It doesn't actually exist. That's why they call it imaginary. And yet in electrical engineering, it is a very helpful thing for your smartphones and all this. They use imaginary space on a chip. That's how they're able to pack these things onto a computer chip. They're actually using imaginary space and imaginary numbers to calculate where things go, and it works. If you've done anything with physics, you know there's something called quantum physics, where either a point of light is here or it's not here, it's everywhere. So it's kind of like there's two realities, and that's, I think, is kind of cool. Anyway, what we're doing is we'll get into that today. I'll give you a few updates. So keep moving along. I think I've got the first set of homeworks due like the 28th or 29th. Is that 29th? And again, don't get too stressed out about it. You want to keep up as best as you can, but I have no problem with moving due dates. In fact, when I was setting this up, I said I could put all the due dates the day of the test. But if you're like me, I wait till I don't have to worry about it. Sometimes I need a little stress to keep me moving in a class. So that's what those are about, is try to get at least I'd like you to get done earlier, but we'll give you till here. And if it's not there, let's move that. But the goal is to be ready for the exam, which is down here. And as I speak of the exam, so that's the goal, is to have everything ready by then. 11, I'll just let you know right now, this thing called the chain rule 11.14 is not on the exam. I would like to move it around. You say, well, why don't we just do the review sooner, do the exam there, and then take up 11.4, and I'd be happy to do that. However, this is a coordinated course, and one of the things they threaten us with is we all have to take the exams at the same week. So if I move my exam to the Thursday, you all find out about what's on the test. They're afraid you'll tell your friends who are taking the test on Monday, and then that's an unfair advantage or something like that. So I kind of like my job, so I thought I'd try to. So some things I stick with. So again, the thing is, if you're struggling, really we only have to go to 11.3. So what it does is it gives us an extra day. Remember, I record the lectures. If you're a kind of person, I don't even want to see stuff that's not going to be on the exam before the exam, just don't come this day. Watch the video after the test or something. So I just let you know that the other class, the Monday, Wednesday, since they're a little bit behind, they don't do this till afterwards because they're taking the test here. So we'll be able to get you to 11.4, but just letting you know, it's not going to be on the test, so you might want to just kind of ignore that particular day until after the test. Okay, so that's kind of getting us where we are. And the thing is that chain rule, it's helpful, but it's a little bit cumbersome. It's complicated. And so again, my first preference would be to not even have it before the test, but we would then be moving things over here. So we'll see. I'll do it, but again, my suggestion is either don't come that day or put ear stoppers in and don't listen to it. And we'll pick it up later. All right. The other thing I wanted to take a look at is when you get into the homework, today's 10.4, there's a few questions like this one that have graphs, and they actually want some, and I found this out from one of the students. He reminded me, they want some really specific details. When you're going to calculate the rate of change here, you're going to find 2 points and find the slope. But they want some of these points, the y value, I can't remember which one they want, but they want it exactly. And if you click on here, this is how it's so this is they have to put these in on every image for people who can't see. A screen reader could read this and tell them what that graph is. Well, it's also going to tell us where the points are, and you'll see there's there's a point at 6, 2.85. How would you ever know, looking at this graph, that it's at 2.85? You wouldn't. You would probably say it's at 3. But if you'd use that as in your calculation, you won't get the right answer, and it'll keep telling you you're wrong, but you're doing the best you can. And I've done this, and I couldn't get it right. And I said, oh, just click on there, and it tells you what the points are. Okay. So if you've already found that out, you're further ahead than I am. But again, with help from students, when you get to this homework, make sure on the graph you click on it, and it will give you the points that you need to do your calculations with. Okay. All right. Everything else going smoothly, reasonably? No complaints yet? Okay. So let's get into this concept that we're now going. So we're transitioning from talking about limits at infinity, and again, what we see is that fortunately they've cut that down, because the rest of the class we use the concept of limit, but we don't have you really calculating them so much. It's just a tool that we need to be able to talk about the derivative. The derivative is slope at a point. It's instantaneous rate of change. To get us there, we have to understand something we've probably all been working on through our algebra, slope using 2 points, slope of a line. That's really what we're doing. So we're going to start there, and this will propel us into the next lesson, which will specifically really get us to the derivative. So average rate of change. So this is a setting. A rate of change is, well, physically what we'd say is maybe our speed. If we're in a car and we go for 2 hours, and in 2 hours we went 100 miles, what was our average speed? 100 divided by 2, 50, yeah, 50 miles per hour. That was our average. Does that mean we were driving 50 miles per hour all along the way? No. We could have, right? But, and if the cop stops you and says, well, I clocked you going 200 miles an hour, you say, well, but I only averaged 50 miles an hour. I made up for it because I went slower here. That's not going to work. But that's what the idea of an average is it's the beginning to end, but there's something different that may have happened in between, and we're going to talk about that. But the average rate is just a measurement of rate between 2 points. Okay, so we need 2 points, and it's the standard slope formula, y2 minus y1 divided by x2 minus x1. So we take our 2 points, subtract the y, so it's a vertical change over the horizontal change when we're looking at a graph. That's all it is. And it's going to, again, be another tool that gets us to the derivative, where we're going to be able to actually get the slope at a point. Okay? So we'll do an example here. Here's sort of a business example, at least if you're into finance. This is a table that shows values for the Standard & Poor 500 stock index. So there's the higher the number, the more value there is there. So that's one of the things people will do. The Standard & Poor's 500 is a grouping of 500 companies, so it's a calculated value of how those 500 companies are doing. So it's really an average, if you want to think of it that way, of what those 500 companies' values have done. And so when those 500, the majority of them are going up, the index will go up. When they go down, it goes down. So we see here in 2008, it had a value of 1,400. It's not dollars, it's points. But it could maybe easily translate into dollars, but it's an index, so these are points. And what we're going to see is that the top is our X value, the bottom is our Y, and so we see that the units that we're going to use, again, slope is always going to be the change of the Y divided by the change in the X, right? So it's going to be points per year. So whatever we get when we get the slope, we also want to understand what the units are. And again, it's easy for me to flip these things, and again, some of the things is, in tables they put the X on top and the Y on the bottom, but when we do the slope we have to do it the other way around. And I'll tell you what, that's one of the biggest frustrations or struggles I had with math, is I typically do things backwards. Okay, and so my slopes are oftentimes with the X on it. So I had to train myself. I had to realize oftentimes when I just try to do it naturally, I would see, okay, X is on top, Y is on bottom, so that should always be, but it's not. So there's a lot of things that change on us, so keep on track of that. And let me remove my little strip. So here's our question. They want the average rate of change for several of values, and we're going to do one of them together. The rest are in the PowerPoint, and it's the textbook company did them all, but I don't like to just click through slides without kind of giving it a verbal walkthrough first. So what was the average rate of change over 2010 to 2014? So again, what we're going to do for average rate of change, we take just the 2 points and we ignore everything else. Okay, because average rate of change is just between 2 points. So you have to ignore everything else. We're going to take a look at that later, but so we'll take these 2 points, and to get the average rate of change, 10, 1, 1, 5, 0, and 14, 1, 8, 0, 0. To get the average rate of change, we, again, subtract the y's in front. So change mathematically is calculated with subtraction, right? How did I change? I grew from here to here. The change is subtraction. So we're going to subtract them. That gives us the change. And then just remember, whenever we're getting an average, we divide. If you want an average of numbers, you add them all together and divide by however many there are. So in this case, what we want to see is what's the change of the X. So the input value, that's how many we've done. So to get an average, we're dividing by the number of years that have gone by. So that's X2 minus X1. Okay, so that's hopefully something you've done multiple times in algebra. Again, being dyslexic, getting the numbers in the right place is always a challenge for me. That's Y2, that's Y1, here's X2, here's X1. And when we subtract the top, we get 650. When you subtract the bottom, you get 4. And 650 divided by 4. I did this yesterday, but I can't remember. So I think it was something like 2 something divided by 4, 162.5. So our average rate of change is 162.5 points per year. Okay, so that means if from the start to the end, on average, we're going up 162.5 points each year. But if you look at the data, that's not actually what happened. The first year we went up 150 points. Is that right? Yeah. Then we went, but then the next year from 11 to 12, it was level, so there wasn't any change. And then it went up by 100 points, so still below but then the last year it went up 400 points. So again, the rate was not 162.5. That's not what was actually happening, but this is an average rate of change. This is what would have happened on average to get to the same output. Okay, so that's what we call average rate of change. We're also going to see that what this produces, we're going to look at the graph of this. It's something called a secant line. We connect those 2 points with the line. We call that a secant line. And secant is some Greek word because it comes from the Greek, so it's a geometry word, and I can't tell you why they call it a secant line or why it works. The good news is we're not really interested in the secant line. We're going to use it as a tool to get to something called the tangent line, which is a little bit more understandable. It's the slope at that point. So that's what we use for the rest of the class, but we'll get through that. So does that make sense? Most of your homework, you'll have a table of values or a graph. You need to pull out the 2 points they're talking about and just find the slope. Difference in y's divided by the difference of x's. That's primarily what we're doing. Again, some of the questions we'll ask you about what's the units on this because this is a business math class. Units are so important because we got to know what we're talking about. A number of 162.5 is meaningless unless I put some units on it, right? Is that dollars per year? Is it points per year? What is it? And so we need those proper units on it. The rest of, so I'm just going to kind of walk through this. This is just doing what we just did, okay, step by step. So it's available to you. If you click on this link, you get the same thing, and this is what the textbook company, so you can see they've got the two values, year 10 and year 14. They've got the output values, 1,150 and 1,800. They subtract the output values, and that's where we got the ones that are the 650. And then down here, they come and say, okay, that was over 4 years, so let's divide by 4. So they got the same value that way. And then they're going to do it again using more of an algebraic approach, using the slope formula. So you can kind of, this is how I went about doing it. It's a change in the output divided by the change in the input. So there's our, again, you're just seeing more symbolic representation. So this is an output value of year 14, output value of year 10. This is what you saw me set up and then do the calculation. So those are the kind of things you're going to do. So, but if I just walk through this, it looks like all I'm doing is reading a PowerPoint, which is really all I do. So what I like to do is show you how I think through them. Okay. And then they ask some other questions. So what's, like interpret the results. Well, it's saying that on average, it was 162.5 points per year. Okay, that's the change. And it was going up because it was positive. We'd see on some of these, like from 8 to 10, it was negative. And so when we do that calculation, again, very similar with different numbers, we end up with a negative value, actually a negative. And so the interpretation is that it's decreasing. So notice it's not, when they report it in a sentence, they don't say it's negative 125, it's decreasing by negative 125, it's decreasing by 125 points. The negative tells us it's decreasing. So watch that in some of the answers when they have you do it. They will put the word decreased, that stands for the negative. So then just be careful, don't put a negative 125, it'll mark it wrong because it really wants just, a double negative would mean it's actually increasing, right? So again, from 8 to 13, we would do the same thing, but we would just look at those points. So we're looking at different points, we're going to get different slopes. And again, multiple ways, you're just going to do this again and again, realizing you're getting the slope, right? And this one, the rate of change in the top, 1,400 to 1,400, that was zero change from the beginning to at least that point, to year 13. So over that span of 5 years, it didn't change. Of course, if you're an investor, we're going to see it actually did change. It went down, so there's some stressful times there, then it came back. But again, the average change over that time period was 0. So what we're going to do now is we'll take a look at the graph. So they ask us to graph the values of the table and see what it looks like and kind of connect that. So we're going to do that. I've got a Desmos activity that I've actually already got set up, so you don't have to see me put these in. In Desmos, though, you can just click on this plus and put in a table, which I'll do in a moment. This is the data that from that table. So year 8 was 1400. We see it dropping, going here. What we can do to kind of see the trends a little bit better is you can do lines and have them connected. So we see what's actually happening. It comes down, it goes back up, it kind of levels off, and then it goes up again. So that's actually what happened. But what we want to see is that calculation we did, year 10 to 14. Was that the first one we did together? Yeah, 10 to 14. So what we can see is what does that represent? I'm going to put in here another setting and just go year 10, year 14, and for year 10 it was at 1150. So I'm not making a new point, but actually let me change this color. Let's make it red. And year 14 is 1800. What's going on here? Let's connect this one with the line. There we go. They just weren't showing up, I guess, maybe because the green goes over the red. So what we got with the average rate of change being 1.62 is that's the slope of the line that connects the 2 points that we were talking about. That's what we call a secant line. Okay, you'll just see it. If you don't remember it, I don't care to test, but you'll see it. So when they're talking about the secant line, that's what they're talking about, is the line that connects 2 points. Okay, so that's always what we're going to talk about. The other line we talk about is a tangent line, and all you have to know is a secant line has 2 points, a tangent line only goes through 1 point. Okay, so that's what we're doing. Okay, and we can see on average that's what happened. In fact, you can kind of see it looks like that on, from this, it's almost all on a straight line. So it seems like after it dropped, it kind of has a similar type slope all the way till it gets up to that higher value. But in between, it wasn't always at that rate, right? It really gets at that rate because of this last portion right here, right? This is what this part here is what really created that. Otherwise, it wasn't performing quite as well. So if we only go to here, we'll get a line like that, so a lot less slope. So it's very crucial that we're using the 2 points that they give us, and that gives us a slope between those 2 years. Where this comes in is, and oftentimes in business situations or whatever, we don't have all the data. Some years maybe the data wasn't being collected or something, but we have this data and this data, and we can just see what happened on average. That's where it's helpful. What we'd like to do, though, for making business decisions is we want to know what is the rate of change today. And again, the only tool we'd have is by looking at the past, but we can't see what the future is going to be. So all we can do is, that's where we're going to go with calculus, is it gives us that tool to kind of be a little bit more predictive, right? Because this one, we have a lot of, depending upon which 2 years we choose, we have a lot of different slopes, right? A lot of different rates of change from 1.62 per year. If we choose 2 other years, we've got a negative. 2 of the years we have a few of the years we have a 0 change. How can we make a business decision based off of that stuff? It's hard because it's either going to go down or it's going to be no change or it's going to go up. yeah, it's like roll the dice and do it. But what we're going to do is we're going to see is that by looking at overall trends, we're able to actually come up with uh, a mathematical model, which is just a fancy way of saying a function, x to some power, and we're going to actually be able to, what we learn in a short period of time is how to take that derivative from the model that was made from the data. Okay, and then that gives us today, because of I've got the model of what's happening, I can predict what will happen tomorrow with some level of accuracy. Remember my former client from Eugene, actually it was Emerald Forest Products of Eugene, made plywood. That's what he was doing, not using the tools of calculus, but just intuitively he got to that point where he could do that. I can buy today, sell next week, and make a big profit without doing any work on it. Or if I'm going to make a profit, I'm going to have to make it into plywood and then sell it as plywood, and that's how I'll make money. Either way, he was going to make money, and he did. Okay. Okay. So this Desmos thing is available to you. If you go into the slideshow and click on it, you can play with it too, which is important because the last one I'm going to do with us that we're going to do today is maybe a good one to play with, because I'm going to show you, and you could do that. Okay, so that's kind of what it looks like. Just remember, average rate of change is not the actual changes year by year, but it gives us the change between two of the points. And so again, the textbook company put together these slides. Here's a graph. I could have just showed it to you, but I wanted to show it sort of interactively, how you can come up with it. You can do it with a table, a bar chart. You can do it with sort of a connected line chart, seeing the trends. And then they go through and, again, calculate the slope between 2 points, between year 8 and year 10. We see we've already done this, it's going down by 125 points per year. And what that looks like is if you connect those two with a line, it's the slope of that line. Okay, so lines are very valuable and very helpful because they're very simple, and they always have the same rate of change. So it's easier to talk about, well, I averaged 50 miles an hour, right? Forget about that time I was going 210 in the residential zone or something. But I live over in Levine, and there's a lot of street racing, so that's, and that people dying from that. So it's not, please don't go 210 in the residential areas. But average is just telling us the whole, what happened from beginning to end. It doesn't really tell us what happened in the middle. Okay. And so you can kind of walk through those slides as you want, but just rate of change is for purpose of the homework. You're going to get 2 points, subtract the y's on the top, subtract the x's on the bottom, divide, and you'll have your average rate of change. You'll have your slope. Again, slope of the secant line. Here's another way to look at it, and again, it just gets you sort of comfortable with the mathematical symbols that are doing the same thing. So instead of talking about, let's go back. Instead of talking about here, this is the same thing as talking about y2 minus y1, but notice it's using different notation. So it's using f of b, which is the output of b, f of a, the output of a, and usually we're going from point A to point B, so A comes first, B comes second. That's all they're doing. Okay, so mathematically, it's just different symbols, and when we're doing it, it's the change of the function output divided by the change of the function input, change of f over change of x. You could easily say, well, what is f? It's really y values, change of x. And this little triangle I'm drawing is it's a Greek letter delta. Delta is used for change. Okay, so that's how we read those little deltas. Okay, so change. And so we see the same slope formula, but we're using different letters, b and a instead of x1 and x2. F of b f of a instead of y2, y1. Okay. And then what we're going to start doing, instead of looking at data, is the data usually, we've got some kind of a function here. Typically those things have been taken from the data, and we do something called regression, which I've taught this class before, well, about 10 or 15 years ago when we taught this class. We would teach you, the first section we teach you was regression. So we'd give you a bunch of data and you'd be doing regression, turning it into equations, functions. We don't do that much anymore, but because the tools have gotten so much better, we just hand you the equations now. So, but that's where they're coming from. You have to see somebody sat, and the statisticians took the data and came up with this function. And so what we do now is we do, and that's where we really talk about the secant line when we've got a function, a smooth function like this, is we're talking about 2 points, again, starting at point A, going to point B, and then it's got, when we connect those two output values, we get a line, we call that a secant line, and the slope of that line is the average rate of change. Okay, so there is some abstractions here. You know, speed is something we can see physically, but we can also put it on a graph, and it's the same thing as if it was the rate of change of dollars over time. That's a different physical activity, but it would look the same on a XY graph. Okay, so that's, again, same thing we're doing, pulling 2 points off of a graph. And remember, in the homework, you may need to click on the graph to see what those points actually are. You may not be able to read them off the graph like I've tried to do myself. Okay. So they walk through here, and on this one, what they're doing is they're pulling these values off the graph. Again, this one has no way of doing that, but they are telling us somehow that they know that when you plug in, if A were 3, you're plugging in 3 to the function, that we get a negative $1 billion. But by year 5, when we plug 5 in there, we're at $0.5 billion. Okay, so again, that might be, we click on the graph and it tells us these values that we need. And again, we're just finding slope, right? The output values are up here. And remember, we're always subtracting, but since one of the values was negative, it's subtracting a negative. In the bottom, we're always just subtracting the input values, and that leads us to an average rate of change, and our units are always in the y units divided by the x units. Okay, so as you read through there, kind of label those. And again, units themselves are important. They are important because that's what gives it meaning. Okay, so just a sort of a different formula. And what I want to do now is let's take a look at an example. Here is a function on the price of gold as it was changing in a given day, from 7:30 in the morning till 10:30 in the morning. So that's what the question tells us: the commodities traders, the price of gold on the market, and this equation works between 7:30 to 10:30, and t, again, we'll change the t to x's because we use x and y on our graphing calculators and such. But that's, if I plug in x, that's the hour of the day. So if I want to find it at 8 o'clock a.m., I would plug in 8 for t, and that would tell me what the price of gold was. What they've done is the price of gold doesn't really follow this smooth curve. We could see it probably looked like this. I guess black on black, you can't see very well. Probably looked like this, but again, some statistician took that data and smoothed it out by making a smooth fitting curve to it. And that's what we'll be analyzing, because then we can use all the tools of calculus with it. Okay. And again, it kind of gets out these spikes and such. They do happen, but again, what we're seeing in general, what is the general trend, we can use this. So what they want us to do is what was the average rate of change of the price of gold, again they give a full story, over the 1.5 hour period starting at 8 a.m. So that means they want us to go from 8 a.m. to 9:30 and find this. So what we do is we would plug in 8 to the function, right? We'd get the y value. We'd plug in 9.5 to the function, do the math, get the y values, and subtract them. What I'm going to show you is we can also we can get those values off of a graph. So again, I've set up another Desmos. Let me turn some of this stuff off right now. So there's our line. What I've done is you'll see this is the function that they gave us. So this is the price of gold, again, from 7:30 in the morning to 10:30 in the morning. It's accurate. This is what it would look like. Similar, I haven't zoomed in. Notice I start at 6. And then I've got 2 points. So Desmos allows us to do a slider. So I can actually take A and I can change it. So they want it at 8 o'clock. So I'll put it at 8 o'clock. They want the B value to be at 9:30. So that's 9.5. Put that there. Okay, and then this actually calculates the slope for us. And it's got the formula here, right? The change in the y's. So we're subtracting the y's in the top, subtracting the input values in the bottom. The one thing this doesn't show us is what those values are, but again, you could plug it in, go to a table using this function. You plug it in, you get your y values. It's the same thing. Here's the x and y pair, calculate the slope. You get that it was 2.5. And then what I've done is I've used the point slope formula here. If I turn that on, it will actually draw the secant line. So that's our average rate of change between those time periods. So it just tells you if you bought at 8 o'clock in the morning and then sold at 9:30, you made a profit, right? It was going up. Although it also tells you probably should have held on longer, you'd make more profit. But that average rate of change is since it's positive, that's good. If we tried to sell earlier, so I can move a point, that's what I like, and that's what I mean by take this and play with it. If I sold earlier, then I'm actually, it's negative rate of change, right? So there's maybe that first half hour it was going down, and maybe I got scared and sold, and I shouldn't. I should have waited. So that's the thing about investing, is you've got to know when to buy and when to sell. And you've got to see, well, it is going down, but I remember, if I have some ideas of what happens on general, again, but we're always shooting to the future. Are we always going to be 100% accurate? No. We might not even be 50% accurate, but using these tools, we might be more accurate than just a guess. Although some people have some pretty good intuition. Like I said, my friend, I guess my client, I never met him, so I guess I can't call him a friend, but I like the guy. He was able to just use his intuition, but in his mind there was probably a lot of math going on, some natural math. But what I want to show you with this is, let me bring it over. Like here, there's no change. I bought and sold and didn't make anything. But if I move one of these points, watch what happens. As I'm getting closer here, that's a pretty good steep slope, right? What do you think is going to happen because I can do this, I can make the 2 points into the same point. What do you think is going to happen? Flat line is one idea. Think of our limit idea. If I'm looking like that on this side, I'm just going to jump real quick to that side. What do you think happens think about the mathematics. What's happening? The y values are the same. If I subtract two numbers that are the same, what do I get? Two numbers in the bottom are going to be the same. I subtract two numbers, I get, what is 0 over 0? It's undefined, it's indeterminate, well, let's just see. Why do you do all this suspension stuff when you could just do it notice as I'm coming up, notice my slope here is like 9.25, but when I get, let's see if I can do that. If I get them to actually be 1 point, actually I think what I need to do, 9.43, let me do this. I think I can do it here. Here we go. So notice the points are exactly the same point, and what's happening is it's telling me the slope is undefined because you can't get slope at a point. Because if you try, you're subtracting the y's and the x's, and you always get 0 over 0, which is indeterminate. But it doesn't mean it doesn't exist. Notice it's not horizontal or vertical. This is where we need the idea of limit, because we can't see it. There is no slope at this point. We need 2 points. But if there was going to be a slope, what should it be? Well, I use this concept of limit as I take one of the points and I go back a little bit. There we go, 9.15. And if I go to the other side, what do I end up getting? I get 9.4. So it's something in between those two. 9.25. On the other side, it was 9.35. What's halfway between 9? And I think I made this so it's pretty close. Like I'm a 100th step one way or the other. 9.25 to 9.35. Halfway between that would be about 9.3. So our guess is going to be if I take that slope at that point, it should be about 9.3. This idea of limits, and we would be right. We are right. Because you can kind of see that slope shouldn't just go away, but at that point, that's what it's going to be. So this is where we've come to, is that we've talked about limits, but we don't really need to use limits. We just need to use the idea of limits, that as we sneak up from the left and the right, if they both go to the same place, that's what's going to happen. Because this is what we want to talk about, is the instantaneous rate of change, the rate of change at a point. We can talk about, with algebra, the rate of change over 2 points, secant lines, but we want with calculus to be able to talk about the rate of change at a point, at the tangent line, the tangent point. And this, with putting these two things together, we can. So most of this has been about trying to make you into a believer that this math actually does work. So all the activities you've been doing with limits is saying, okay, makes sense. If I come from the left and the right and I had these two slopes, it should be about halfway, in between it, because that's what I've been doing numerically with these other things, and that's exactly what we want you to do. What we're going to do is, as we move forward, we're going to pick up some tools where we don't look at the graph. We don't have to do this numerically, although we could, but we're going to be able to actually have some tools that allow us to, as long as we know what the function is, that there's going to be an easy calculation here. And I'll tell you, it's just about, we're either, calculus really comes down to being either adding one or subtracting one. This first half of the course will be subtracting one from the exponent, subtracting and multiplying. If you can do that, you can do calculus. The second half of the class is adding one and dividing. Not a big deal. But it doesn't mean it's easy, but that's the technique that we use primarily for getting the derivative. And then the second half of the class is using what we call the antiderivative. So we start with the derivative and we go backwards. So sometimes we've got the data and we want to know what the rate of change is. Sometimes we know what the rate of change is and we want to know what the data looks like. That's the two tools we get here. So it's really cool. So sometimes we don't need to know the data, but if we know how fast... If we know what the rate of change is, we can put that together and figure out what we have. Okay? Turn this. And I think that's almost to the end. And then again, they walk through it. So you can follow this. You can see they're plugging in the values, getting the y value. So they get the y values. They subtract the x values, the 9.5 minus 8, which that little thing did. Here's the calculation. And they get the 2.5, which the Desmos did for us because I had it set up. It's taking that function and it did it all behind the scenes. So that's what our graphing calculators are doing. I just want you to see that here's the sort of step-by-step paper and pencil way. But what we want to be able to do is use our technology, but we also want to understand what that technology is doing. It's just finding two X and Y values and finding it. Okay, and so price of gold on average between these two time periods increasing about $2.50 an hour. So that's good, I guess, if we're an investor. Unless we're looking for it to go down so we could buy a bunch, but if we own it, maybe that's a good thing. Okay. Oh, that's the last slide. So that's what I was meaning. But that's what I want you to do. So in 10.4, this homework is going to just have you find a lot of average rates of change. They'll give you some data, take 2 points, find the slope. They'll give you a graph, take 2 points, find the slope. They'll also ask you about the units. Remember, it's the Y units over the X units. That's what we're going to get. And that's what this one is completely about. What we're going to do is in the next lesson, next week, we start taking into a little bit more. We're going to go to the tangent line so that we can get not just the average rate of change, but the instantaneous rate of change, which allows us better tools for making business decisions. All good? All right. So are we on time or are we ahead of time, behind time? We got like half an hour. So if you got questions, hang around. We got the room for the rest of the half hour. I'm happy to help you. If you want to head out and take a break, that's good too.